Hi, everybody. My name's Alex. Very happy to be back here at Stanford giving this lecture, which I get to give every year, is one of the highlights of my year. Like Dan said, I'm currently the Chief Security Officer at Facebook. Before that, I was the CISO at Yahoo, so I had pretty much the same job at Yahoo. Before that, I did a lot of startup stuff. So I started a company in 2004, sold it in 2010, worked for that. So if you guys have any questions at the end, I've seen both sides now of big companies and little companies, and happy to talk to you about that kind of stuff. Just an FYI, so we're doing a little experiment that my team hasn't done before. We're live streaming this on Facebook Live. So if you ask any questions during kind of the lecture part, your voice can show up. So I just want to tell you that if you have any questions and you absolutely don't want to be heard, then you can wait to the end. At the end, we'll turn the stream off, and we'll have kind of private Q&A time. So kind of want to start with trying to figure out why you guys are here in this class. So I have a couple of theories of what would draw an undergrad. I don't have the same experience in that when I was an undergrad at the little dirty public school across the bay, that we didn't have an undergrad security class, and almost nobody did. I had to take graduate classes and graduate seminars to learn anything about security. And at the time, that was really just something that I was kind of pulled to by the fact that that's something I've been interested in since I got a Commodore 64 300 baud modem, which is, it's impossible to describe to you guys what the internet was like in those days when you could type faster than your computer could actually send data. And so you could type, and then wait as the buffer caught up between your typing and able to set down the modem. But it interests me that there's 300 students in this class, and I think that's a fantastic thing, because as we'll talk about in the end, I think information security is one of the most impactful, the most interesting things that you could dedicate your life to in an engineering field. And so I really, while we talk today, and I hope you leave with, I really want you to kind of think about why you are doing what you're doing. Not just being in this class, but why you're studying an engineering field, why you're interested in going into computer science or systems engineering or double E, or whatever kind of specialty you're interested in, and what you want to do with it. Because if I could go back and talk to my younger self, I'd probably tell him to be a little more thoughtful about understanding from the beginning why I was doing what I was doing. So what we'll talk about is, we're going to talk a lot about how bugs are found in the real world. That's kind of the academic part of this lecture. We'll talk about some different techniques that people use to find bugs in our products, other people's products. And then I want to give you examples of real bugs. Some of those are in our products, some are in other people's, and talk about the impact that they had. And then at the end, we'll talk more about kind of career stuff. And we should have, I'm going to try to make sure to have 15, 20 minutes at the end, so we have more open discussion. If you guys have any questions about security or Silicon Valley in general, I would love to take them. So how are bugs found? So I'm sure you guys still learn in the beginning of computer science the idea of a state diagram, right? Of the idea that you can represent in a very simple program all of the different states that program can go to, right? So in this case, those are the little gray dots here. And the lines between them are the different transitions between them, right? So I go from one state to another based upon input or other kinds of things that are going on in my computer. So the basic problem of where security bugs come from, the reason that we have security bugs, is because there are concentric circles of state that some of that stuff is covered and some of it isn't by anybody who develops it. And the truth is, for modern software, this would be simple state diagram even for like a beginning CS class. Any modern piece of software cannot be described except with a functionally infinite screen of state, right? Like there are programs, software that is being written today will run in situations where the entire state space of everything that program can do will never be explored in the history of that program running, right? And so the way software is written is that you generally have kind of the states of the ways that a developer thinks should happen, right? So if you're developing a piece of software, you're doing it for a specific purpose. You've got some kind of design spec. You sat down and these are the things that are supposed to happen. And so you write your software as to how it's going to happen. Then if you're a good developer, you're also writing tests. And those tests are going to cover, at a minimum, the kinds of things that are expected to happen when somebody pushes a button. So if I push a button and a box pops up, then certainly I'm going to have a test that if that button gets pushed, that pops up. And if you're working for a big enterprise, that test will be something that you're required to write to even check the software in. So that's like what you're thinking of when you're writing the software. Good developers also then think about all of the possible things that might happen when deployed in the wild, right? And it used to be this used to be called quality assurance. Back in the dark ages of software development, like the 1990s, people writing the code thinking about the middle were different than people on the outside. That's almost not how anybody writes software these days. Today, there's a lot of test-driven development where continuous integration environments where you're perhaps even writing the tests first. In a lot of different modern software engineering techniques, you write the tests to make sure the software is working how you want first. You test the tests, and then you write the working piece of software to fill up the middle of what you expect. And so this is what most engineers, good engineers, are going to be thinking about, are what are the things that can possibly happen? So if I got my super simple software, and I push the button and a box pops up, and that's all supposed to happen at this point, what happens when I push around it? What happens when I push the button many, many times? What if I push the button, and then I go do something else? The software gets interrupted, and I come back. Is the box still there? Those are the kinds of things that should be properly tested and thought about by the engineer. What you're looking for if you're a security engineer, or a person who's a security researcher who's trying to find bugs, is you're looking for the state of what an attacker can make happen, which is, there's often these, like this little red dot here. This is the state of vulnerability of something that was not foreseen by the developer that would never accidentally happen. In this part, you should be covering everything that's like basically a monkey typing on a keyboard, right? Like anything that, which is what it's like to write software for a billion people, is you can imagine people banging their heads against the keyboard continuously all day, and that's the kind of problems that you're gonna get. This is trying to find a state that, if you very, very carefully manipulate the software, you're able to get to a vulnerable state. And this is really just the basis of all security research, is trying to find where this is and how to get there. Now, there's a couple of ways you can do that. You can try to find all the ways around, or you can try to find where that is, and then figure out how to get there. We'll talk about those different paths. So, the vulnerability discovery is pushing into exploitable states, predicting the kind of mistakes that somebody will make. So if you know how software is built, if you know how engineers work normally, if you're an expert in the kind of technology it's being built on, whether it's mobile or web, or a thick client app, then you'll have the understanding of the kind of mistakes that are commonly made. And then the real key part of vulnerability research is making the impossible possible. And this is where there's kind of a great, rich history, if you read about the bugs, that people said were not exploitable. That can never be exploited. That can never be put into an exploitable state. And a ton of work going into one person figuring out once, and then that technique being used over and over again in the wild to hurt people. So one of the kind of classic ways of doing this is a technique called fuzzing. Fuzzing is the idea of using automation to explore all the state space of a program by giving it all kinds of bad inputs. The oldest fuzzers were really, really dumb. They just take some kind of pre-made input that is known to work for a program, and they randomly flip bits in that. Why do you think that is dumb? Why is randomly flipping bits not the most efficient way to do anything in fuzzing? Anybody have any ideas?
Because it's a very specific path you need to go down where it's useful and randomly change stuff.
That's right. So if you need to get to that very specific path that we showed, all the way corner, randomly bouncing around that state diagram is not going to work very well. Where do you think fuzzing of just like random bit flipping often fails for people? Anybody know what a Word document actually is? How a Word document is laid out, a modern Word document? When you save a Word document, what's the extension?
DocX.
DocX. Anybody have a Word document on a Mac right now?
Mm-hmm.
Type file and then space and the name of the Word document. And tell me what the file command tells you that Word document is. What it's going to tell you is that it's actually a zip file, right? So a Word document is a directory structure with a bunch of folders, and each of those folders are subfolders, and then there's a bunch of XML files in it, right, with totally unreadable names. And so what Word does is it puts a bunch of data together, and then like if you embed an image, there'll be a folder, and there'll be an image with the .png in it. And then there's some kind of master file up here that tells the Word how it's all put together. And then this whole thing is put together, and it's put into one big zip file. What happens if I just start flipping the bits in this zip file randomly? What's the process that Microsoft Word undergoes to open up a file? What's the first thing it does?
Decode it.
It decodes it, right? What's it do to the zip file?
Checks it's valid.
Yeah, so it checks it's valid, right? And so zip, just like every other compression format, has some kind of basic checks to make sure it has not been corrupted, right? So if you take a thick, complicated file like this and you just start randomly flipping bits, what's going to happen is if you look at the code paths that Word goes down, is there's going to be this big, not that big, a small amount of what will be highly tested, carefully written, artisan code MP4 player or a thing that reads pings. And obviously, you've got like an XML decoder. There's been all kinds of fun bugs in XML decoders. But if all you're doing is flipping bits, you're just going to get stuck in this little piece of software up front, and you're going to get that box that pops up saying this is like a corrupted file over and over again, right? And so that's the classic way of doing fuzzing. People have come up with much more intelligent ways to do it, such ways that understand the file format and that put things back together in a way that's very careful. Like in this example, let's say I want to attack the XML parser. What am I going to do? What's my fuzzer actually going to do?
Unzip the file?
Yeah, it's going to unzip the file, write it down, take that XML file, make a change to it that I think is bad, and then put it all back together. Other kinds of advancements, the kind of state-of-the-art that you can get off the shelf to do this kind of stuff is a thing called American Fuzzy Lock. It's written by a gentleman named Michael Zalewski at Google. It's a fantastic, interesting program, and I definitely recommend you go look at it and then read the documentation. And we'll talk a lot about these kinds of things, about doing file fuzzing. The other thing it does that's really interesting is it watches the control flow. So to do this, you actually have to recompile the software, or you have to instrument the software to watch what's going on the inside. And so it will watch the control flow of a piece of software and then track whether or not the fuzzing is getting into parts of the software that never been explored before. And then if it makes one little bit flip somewhere that gets into somewhere totally new, it will continue to explore that space. Another way to do this is a technique called reverse engineering, which is actually what it sounds like. It's taking a piece of software and figuring out how it works, finding the bug, and then working backwards. So this would be like looking at that whole bullseye document diagram, finding the little red dot in the corner, and then figuring out how does software get to that red dot. The classical way to do this for thick client apps is a program called IDA-Pro, which is a disassembler. So it turns the binary object code into assembly, which is assembly is human readable, but it's a one-to-one mapping of what actually executes on the processor. So it's basically the lowest down that any normal human can go and look at a program. And the great thing IDA does is it will then help you turn that assembly into something that's much easier to understand. So it gives you things like control flow. It will tell you these parts of the program are going to different places. These are the functions that are calling each other. It will pull out debug symbols. So if this thing was compiled without the exact right settings, there might be extra information in there that IDA can use. And so a common thing would be to have a macro written in IDA's macro language that will find an exploitable situation, and then that allows you to step backwards, and try to figure out how to get there. Other ways you can do this is disassembly. I'm sorry, that's disassembly. Is debugging. So debugging would be to do the same kind of thing, but on a running program. So if you have a piece of software, like say a mobile app on an Android phone, you can root the Android phone, you can attach a debugger, and you can watch the execution of the program as it goes step to step, pause it, look at memory, look at the control flow, look at what's going on, find an exploitable situation, then try to work your way backwards. This is often how people do exploit development, is they attach a debugger to a vulnerable system, they give an input, they watch to see how far the exploit went, see that it did go somewhere, they back it up a little bit, change their input, try it again. Over and over again until they can figure out how to get to that corner. And then binary diffing is actually something that was super popular back in the days when most of this stuff was happening on Windows, which is taking patches that people put out and then figuring out what's changed. This is why a lot of the interesting politics around patching exist, because it turns out if you're a company and you know about a bug privately, the best thing you can do to get people to exploit that bug publicly is to issue a patch for it. Because there are teams that, like when Microsoft releases their patches, that take the patch, run it through a bunch of automatic binary diffing, find what Microsoft changed. That's a big arrow saying that this was an exploitable thing in the original code. Do debugging disassembly, and then walk back and write exploit code. In fact, there's a bunch of academic research to do that all automatically in seconds instead of a human having to do it over hours. And so that used to be a more popular thing. It's less popular these days because with things like mobile devices and such. Because people don't release the way things get patched is a little bit different. But there's a program called BinDiff that used to be very, very expensive and is now for free that I totally recommend that you try out. Install BinDiff, go get a Windows patch, go run it against the existing DLL, and you will very quickly be able to find all the interesting security bugs that were patched, some of which were publicly documented and some of which might not be. And then in the end, a lot of bugs, especially these days, are from manual manipulation. which generally comes down to asking a piece of software to do something that it doesn't want to do, but asking it really, really nicely. And this is what a lot of web bugs, a lot of the bugs that we have that people find in our products are of this kind of problem. They come from a number of different places. Confused deputy is the idea that the software is confused about who's asking it to do something. This is a common problem either in complex systems where you have to pass authentication through to multiple parts, that you can ask it to do something. Has anybody here heard of like a SQL injection attack?
Not yet.
Not yet, but several people have. It's amazing they can learn things, even if they haven't had the lecture yet. I'm very impressed. SQL injection attacks, I mean, the whole class of injection attacks actually come down to kind of a confused deputy problem, where you're able to pass commands through a program that talk to another program, in this case, a database, and the program on the back end can't tell what part of the request came from the legitimate code and what part of it came from the attacker. There's also another kind of web bug called cross-site request forgery, which utilizes how web browsers work to have the same kind of attack, where you're put script into somebody's browser, and that request makes that script makes a request on your behalf using your cookies. And then on our side, we can't tell what legitimately came from you and what actually came from the attack code. The attacks like this often require people to have tooling that allows them to intercept something that's going on and to change it. So if this can be either in like a standard format of something like web requests and web services, in which case things like Burp Suite work well. There are also tools that do the exact same thing on like thick binary protocols. If you have a thick mobile app and it's talking to something another piece of software over something that's difficult to understand, it will decode it and allow you to make those requests. So Burps are great. There's a free version. You can play with it. It's a great tool to play with if you want to see how web apps actually work. It sits between your web browser and Facebook or whatever site you're going to. And it will intercept every single request and allows you to pause those requests, to look at the details of them, and then to make changes to them, like change fields, change formats. And these also has a fuzzer built in and other kinds of tests that will test for obvious, often seen web application vulnerabilities.
Alex, isn't Facebook over SSL?
Facebook is over SSL. This works generally because you're running this browser locally, and to make it work, you have to install a certificate locally that you have signed your owner's certificate authority, and then it does an interception. It pretends to be Facebook, so it will get the connection, decrypt it, re-encrypt it with a connection that has been authenticated with a certificate that is theoretically only local on you. There's actually been a whole class of bugs where these kinds of products use the same certificate authority everywhere, and therefore create a security vulnerability if one person gets a cert, and then they can break into anybody's connection anywhere. Generally, the professional security tools like Burp will not have those kinds of problems. It's also interesting, too, that this is an interesting problem where we try to tell the browser to not allow this to happen, but the browser allows itself to be overwritten by local, which is an interesting political discussion that happens in the professional industry between people like us and people who make web browsers. So, putting it all together, let's talk through finding one bug. So, let's say we have a thick client application that runs on OS 10 or Windows. Doesn't really matter. Let's say OS 10. It's a Unix program that we've downloaded, and we've wanted to look for security bugs in this program. It takes some kind of external output, and we think we can find a bug that we can exploit. We drop into IDA, and in IDA, we can go and search for function calls into well-known functions that often have security problems. In this case, we've searched for a function called printf. Anybody know, I know you haven't gotten there yet, but does anybody know from their independent study up to this point, what kind of security problem can be caused by a printf call?
Well, I think most the simplest, like string format vulnerabilities.
String format vulnerabilities. That's right. So printf is a beautiful universe as to itself, right? You'll find this a lot in both Windows and Unix worlds, where people put lots and lots and lots of functionality into what should be pretty simple function calls. So it turns out printf does what you think it is, which is it prints out. It can print out to a file, it can print out to the screen, but it's the format data, and to turn it into a serialized format. You can call printf, if you call it with one argument, and you just put a string in there, it will take stuff that is in that argument and it will interpret it, using variables that are then given to it elsewhere on the command line, right? So if you send printf like, I will see you at $, or %s. What it will do is reserve space here for the next variable that it's given and pop it in there and format it, right? So this is how you can say, I will see you at a variable, and you can dynamically put together a line. It turns out there's a huge number of interesting things you can put into this place where %s. And what that allows you to do is to manipulate printf to manipulate memory up and down the stack, and to read and write arbitrary memory different points in the stack. We're not going to go into detail. I think you guys will go into detail about how that's exploitable. But what we see here is we see a printf call, and when you learn what function calls look like in assembly, what you'll learn here is that this is what's called a naked printf call. A format string is not being pushed to is not being put in the right place on the stack for printf. Therefore, printf is going to be exploitable to a format string bug if you can control the string that goes to it. And so the next thing you might want to do is you might want to try, let's say you've done some disassembly, and you see that this printf call is used all over the place, that this function that has this printf call is used all over the place. And therefore, while you could go and manually trace it, you're thinking to yourself, this might be a great situation where I want to try some fuzzing, because this function can be called from all over a bunch of different inputs in these files end up there, and we'll see what happens. And so now we're going to run AFL, which is the tool we talked about before. This is a specific subtool AFL has, which is really cool, where you feed it a file, it will look at the format of that file and try to figure out interesting parts of that file to fuzz. So it will say, this looks like a checksum, and this looks like an unsigned integer, and this looks like a place where a string can be placed. And so you'll run this, and then it outputs a config file that then you can do a bunch of manual configuration on. So you'll go do that, and you'll do it. You'll go configure AFL to especially test for format string bugs. Maybe you do that, and you'll get a crasher, right? So you'll get a dump out of process memory space, or you've had a debugger attached, and it will crash, and you'll be able to explore the memory space. You'll be able to see the stack trace of how it got there. You'll be able to look at the file that caused the crash and where that format string bug was inserted. And so now you will go open up a file that you want to use that's not malicious yet in a hex editor, and you'll go edit it to put in the format string bug. This is a popular hex editor called 010 that you can go download. I think it's generally paid, but I think they have a free trial. The cool thing about this one is that you can have templates that will look at a file and then explain to you what it is, so you don't have to edit the file totally raw, just in hex. It will help you figure out what you're looking at, which is super useful in these cases. And so you do that, and then you have your file, and you have a file that you know that if somebody opens it up, it passes all the way through to that printf statement. Any questions on those kinds of techniques? We'll have time at the end, too. So let's talk about some real-world bugs that people have found through a couple of these. So this first one, this is a bug in Facebook that was a real fun one. That comes down, the technique this guy uses, the manual manipulation technique, that he just went and basically asked us to do something that we shouldn't have said yes to. We have this a caution issue. A common issue in web applications is if you have multiple things that are being shared between different people, of understanding who owns what. Basically reference counting, of knowing who owns different binary blobs or different pieces of data in the system, and therefore who has what access rights to it. In this case, what this guy figured out was that if somebody posted a picture, like including their profile picture on Facebook, that he could include that picture in a comment later. And we don't just re-upload that picture. What we do is create another reference to that picture so that we only have one copy of it. If this guy has reposted the same picture. The unfortunate thing we did there is we didn't quite remember that somebody else actually owned it. And so what he could then do after posting that picture in the comments is delete the comment and delete the picture itself. In this case, he made himself a little bit famous by deleting Zuck's profile picture, which was an interesting way of getting our attention, but often very effective. There have been a couple of more bugs like this since this guy came out. You can go search for this on YouTube, and you can go watch the video, and it's kind of fun. It's kind of boring to sit here in class and watch it, but we have more time. But this is a kind of a common issue of if you have a very complicated security model like we do, and you have all of the different pieces of content that exist, and different people can edit them, and different people can post and share, that you have to remember kind of the history of that object to make sure that people aren't able to have access to it. And this is often kind of becomes a copy on write kind of situation, that if you have something that multiple people can share and edit, if they want to post their own version or do something, that you make a new copy of it, therefore they can, if they delete it or something like that, it doesn't affect the original. But that's difficult to do at scale because obviously that can cause all kinds of performance issues. The next one is a pretty famous bug in Apple's TLS code. So take a look, nobody yell it out yet. Somebody find, everybody take a look and see what they can find where the bug is. Okay, I haven't heard from anybody on this side. So somebody on this side point out where the bug is.
That go-to field is like connected, but it's not part of the if, because there's no breaks.
Right, so there are two go-to fails in a row, right? So this was pretty clearly a copy and paste error by the original engineer. I don't give you all the context here because it actually takes a bunch of code to understand that. But the context is this is the part where they are checking, the software is making the decision of whether or not an SSL certificate that's been given is actually valid. And so it goes through multiple steps here where it updates, it runs this update function on different parts of the handshake. And what this is testing is whether or not it is creating understanding of an SSL hash SHA-1, a variable, it is updating the variable of whether or not this should be trusted. What happens with this go-to fail is when this is going to run every single time, right? Because it's not under an if. The program goes, it goes to if, and then it just, this is the end of the if right here, and so go-to fail runs. Now you would think that that would mean that the whole thing would fail. What it actually means is that it goes to a different part of the code, and it hasn't yet run this last step, which is the final step to figure out whether the handshake was good or not. Therefore, it would accept any SSL certificate, no matter how, for a number of different kinds of invalid, a number of different fields could be invalid in the SSL certificate, and it wouldn't be able to verify that before here. The output of that meant that for a long period of time, there's pieces of Apple software in which you could do a man-in-the-middle attack by using a fake SSL certificate, because this go-to fail was getting hit every single time. We can get the source code for this because they also had that code in some of their public source, but it also existed in their private repositories. This is a fun one. So a constant problem of web apps like ours is cross-site scripting, which you guys are going to learn about in more detail. The basic gist of it is we don't want JavaScript running on our website under our domain that we didn't write, right? That is very difficult for a site like ours that is built around people sharing content. So if you run a social network or a discussion forum or any place where messaging app, any place where people are sending content back and forth, one of the things you have to do is you have to look at that content and make sure there's no executable script in it and strip it out. There's a whole interesting history around trying to strip out executable scripts. It turns out there are an amazing number of ways to convince web browsers that something should be executable. One interesting bug that a number of people have exploited is it turns out you can embed JavaScript into image files and then do things to trick a web application into loading that image file not as an image, but as an HTML file. And so the output of this, of which, again, this is a great write-up. This guy reported this via our bug bounty. So he reported this bug, we fixed it within a day. We paid him, I think, something like $5,000, but he made several $1,000s from this bug. He did a great write-up of all the things he had to do. It actually wasn't that simple, but in the end, what he was able to do was get this file up to Facebook, and then create a URL that's under facebook.com, which means it has our real cookies, which is the thing we really want to avoid. And when somebody would go to that site and look at the PNG, he was able to trick the browser into thinking that PNG was an HTML page. So it's like, oh yeah, here's some junk language, and then it hits the script and runs the script, and that's what you're seeing here. That pop-up box is generated by the script. This is what, when you do cross-site scripting, generally the way you test it is you try to pop an alert box. The outcome is often, for some people, if you report a cross-site scripting bug with an alert box, then all they do is they try to catch all the alert boxes, which turns out to not actually solve the problem. It just makes the proof of concept not work. Yes, sir?
So was that malicious image file actually well formed, even though it was changed in some way?
This one I believe was well formed because it had to make it, I believe this one made it through one of our re-encoding pipelines, which is the tricky part here, is trying to push up an image file that makes it through all the steps to make sure something actually is an image. But I'm not totally sure. I would read the blog in this case. Here's one of my favorite bugs. This is a bug that was found internally. Has anybody here heard of FFmpeg? Yeah, stop pirating movies, guys. It's not worth it. You're still young, and you know, back in my day, you had to pirate movies, but now you guys can get them all for like whatever, $3.99, 24 hours from Amazon. FFmpeg is probably the most popular open source video manipulation library out there. It's used by people to encode videos on their home. It's used in professional video production. For us, we use it for something pretty important, which is we use it to re-encode the videos that are uploaded to Facebook. We do that for a couple reasons. One is for space optimization. Sometimes we'll make multiple copies of one video in different formats depending on who's going to see it, and we store all those copies. We also want to re-encode to make sure it's efficiently encoded. So if somebody uploads something that is a very inefficiently encoded video off their phone, because their phone has not a great CPU, they'll upload it to us. We'll re-encode it using a really powerful Xeon processor in a data center, and that we will spend a little bit of time doing that, but we'll save a bunch of space. That if we're holding that video forever, that kind of adds up, right? And when you're trying to store everybody's home videos forever, it turns out you're talking about lots and lots of storage, right? With E's, not P's or T's in front of them. So we use FFmpeg for every video that gets uploaded to us. An interesting bug that one of our guys found is FFmpeg is a very, once again, like printf, has lots and lots of features that people don't really know about. This is from the official FFmpeg documentation. Is the list of all of the different protocols FFmpeg supports for pulling in external content. So it turns out there are a bunch of different file formats where you can say, I want you to go pull in something else from somewhere else. And so we can do that over the internet and such. The one we're really interested in is the one called concat, which read and seek from any resource and sequence as a unique resource. This basically allows you to concatenate into a video any file that FFmpeg can get to. So you guys are probably starting to see where we're going with here. So what our guys figured out was you could generate a M3U file, which is a MP3 playlist. So this is the kind of file you might create if you rip a CD. It will create a bunch of MP3s, and then it'll create an M3U, which is kind of the playlist of all of them with some metadata in it. So you can create an M3U file, rename it MP4, and we would accept that as an uploaded video and hand it to FFmpeg. FFmpeg would ignore the MP4 and be like, this isn't MP4, this is M3U, I'm going to do whatever it's asking me to do. And in this case, what it asked it to do is, please go take the password file and put it into the video. And so the effect here was, anybody at this time could upload this file to Facebook. We would re-encode the video, which means that this code would now execute on our video re-encoding tier. And then we would post a video that had the SE password file from that server scrolling by slowly. Unfortunately, I wasn't able to find the original video, and we can't recreate it because we fixed the bug. But this is one of those great situations that you get, especially in the use of open source software, where people build all kinds of functionality in that you never know has existed, and you kind of have to know what's the functionality of software that you're going to use. There's also, there's a couple different things. There also should be, if you upload an MP4, we should make sure it's an MP4 before we just start handing it to places. This is also a reason why people should do process isolation. And in our case, we actually do isolate these video encoders pretty well. So you wouldn't be able to steal too much data, but I think the idea that you could just basically ask us, please generate a video of your password file, I think was kind of fun, or any file that FFmpeg could get. And then there's a whole class of interesting bugs caused by memory management in PIC clients, especially in code that's written in C or C++. I know you guys are going to cover a lot of this in a future class. When you, either now or when you get to that class, I definitely recommend reading this blog. This is a fantastic write-up of several bugs that, when put together, can be turned into a privilege escalation attack on the Linux kernel. So if you're running in Linux, you're a low-level user, what you basically can do is you can ask the Linux kernel to create a kind of a secret key hidey hole in the kernel to hold a small amount of data. The thing that counts the number of references of what has been created turns out to be a unsigned int. What does that mean if you go, how big is an unsigned int? Both on 30, if I just write int in C, what does that turn into on both 32 and 64-bit processors? Anybody know? A 32-bit unsigned int. So what happens when that int goes past 2 to the 32? It wraps, and it goes back to 0 and it starts counting up again. And so what this is a very interesting attack where you basically can ask the kernel to create these objects over and over again. You do so about 4 billion times. And then because that integer wraps, it loses track of how many it's created. And then you can get it to delete the object and then to get that pointer to point to an object that you control. And now you have process execution within the kernel. Anyway, real slick bug. It's a couple of bugs put into place. It's technically a USEP-free bug, but you have to do an integer overflow to get there. That's why it's kind of sexy. It's a really good write-up too. This is the kind of bug that you might catch with fuzzing, or you might not. Integer overflows, in a situation where you're giving an integer, are easy to catch with fuzzing. And you'll often see fuzzing tools will look at something, a piece of data, and like, that looks like a 32-bit integer, that looks like a 64-bit integer, or that looks like a byte. And then it will put special numbers in there that are there specifically to try to trigger a crash. Numbers that, if represented in the wrong way, will be a negative number, will be a 0, or cause an overflow. In this case, you had to actually do something 4 billion times, so the exploit takes about 20 to 30 minutes to run. And so it's not the kind of thing that you normally would actually catch through fuzzing. And so probably more like something like static analysis, or looking at the code, or looking at the source code is the way you find this. This is a very difficult kind of bug to find, and you can understand why something as complicated as Linux kernel would have it. Great. Any questions on some of those bugs? Yes, sir.
About the open source projects at Facebook, how do you guys manage, using these external libraries and making sure that what you run is good? Like every time you pick a new open source project to use, do you kind of go through and vet it and put work into?
So that's a great question. What do we do to make sure that open source is good? We do some vetting, but this gets very, very difficult. I mean, if you look at all of the open source that's running on any large production network, if you just look at the operating systems we run, you're already at a point where we cannot have a high degree of confidence, right? And so part of that is being careful about what we import. Part of it is then handling those imports well. For example, there was recently an issue with the Node package manager, where some guy got pissed and rage quit writing Node packages. And so he deleted his packages, but what people figured out was, one, that broke thousands of people's builds, because all of a sudden these basic packages weren't there that a lot of people depended upon. But then he had opened up the namespace for other people to squat. So anybody else could have come in and then placed their own malicious Node package in there and then pulled into these projects. And not so much us, I hope not us, but there are a lot of companies where people, when they run a build on their desktop, are going out to the internet and pulling these things down. So that's one of the things you need to do when you use open source, is make sure you have your own copies of repositories, and you're not going and pulling down from random open source servers around the world, because your now network of trust of people who have execution on your production systems is extended to all of those crappy little servers that are like unmanaged Linode VPSs, right, in Sweden or whatever. And so that's part of it. Part of it is looking at them. Part of it is doing security testing in situations where we think are very possible. The other thing that we do and other big companies do is we do have people that look at open source projects, that fuzz them, that provide security patches back. A lot of the bugs that you find in popular open source actually come from professional security teams at big companies that are finding those bugs during their own testing and then kind of get them quietly fixed. And we're actually talking to some companies about whether or not we should divvy it up better. To make sure that we're getting good coverage. Because the problem is everybody's going to be kind of attracted to the same ones that are obvious, and there's all of this not obvious open source, and I think that's something that we have to do better as an industry, is figure out the non-obvious things that we pull in all the time that we're dependent on day to day. Any other questions on this before we yes, sir?
So I'm just wondering on the MP4 bug that you talked about, did you do anything beyond just checking the file is a valid MP4 to fix that, or did you...
The FFmpeg?
Yeah, FFmpeg.
So I think we started checking on the input.
Right,
we probably recheck to make sure our isolation's good. So what we really should do is, you can't trust something like FFmpeg, right? A piece of software that binary movie and music formats are extraordinarily complex, and the encoder systems are built for super high efficiency, and they don't do generally a lot of sanity checking. So they'll do things like blind casts of pointers and stuff like that are extremely dangerous. And so code like this, we have to not trust. And so I think we did some input validation to make sure it's not that. I think we wrapped it to make sure that FFmpeg didn't have the ability to do certain things. If we're going to bring something like this, then it's going to be like that jail in that X-Men where Magneto's in the basement of the Pentagon, right? You got to put FFmpeg at least 100 meters away from any pieces of metal. And what I think we did specifically in this too is our guys went through and they recompiled, they went to the source code of FFmpeg and they tore out all that crap that we don't actually want, right? Like, I do not want my servers doing a Gopher connection out to some server in Romania and pulling down executable code. Anybody here? Has anybody here used Gopher other than Dan Bonet?
Thanks, Alex.
Oh, okay. Yes, sir. You're looking great for a 27th year undergraduate.
So, Alex, we talk about jail and isolation and confinement. So
Yeah, jail isolation time. So there are a lot of options, especially these days, to isolate a piece of code that's untrustworthy to make sure it can't do bad things. That can be in the Linux kernel itself. So there are a bunch of extensions to Linux that allow you to basically build kind of kernel firewalls. You can look at the kind of things that any process does. And even if they're running as root or running as a high-powered user, there are certain things that now the kernel will not do on its behalf. And so SE Linux is the most popular one of that, and I believe that's what we generally use for our jails. The other thing you can do in those situations is you can run these things in containers, which run under LXC, which is another way that you can tell the Linux kernel to run this program but treat it as something special, or you can run them in virtual machines. Virtual machines actually turn out to make very poor isolation mechanisms, because what you're doing is you're trading the admittedly very complex Linux syscall interface as your attack surface for C code that is simulating a sound card and a south bridge and all the other stuff that needs to get simulated in GPU in a full virtual machine. And so virtual machines have actually an interesting history of people breaking out of virtual machine jails. I would probably recommend running like an LXC, or probably most likely, something like LXC plus SE Linux would get you in a better place. LXC for more of like, you can use an off-the-shelf container system to make it easy to do it, and then use something like SE Linux to really harden to make sure this process can now not do anything very dangerous. Cool. So different kinds of people are looking for these bugs all the time. Obviously, you have the defenders, the people who work for the companies or the open source projects who are building the code themselves. The benefits these people have is that we obviously have full access to the code, even if it's a shipped commercial product. We have access to the engineers. The downside that we have is that we want to have 100% coverage, right? So it is not enough for us to find 5 bugs and be like, look how awesome we are, we found 5 bugs. If there's a 6th and a 7th bug that are absolutely horrible and terrible and something bad really happens, right? The coolness of the 5 bugs we found does not get us get out of jail free card for having significant problems in our software. And so that's why on the defense side, people are generally looking for doing 2 things: going deep in situations that we think are very dangerous, right? So if we're, our code that handles encryption, our code that handles cookies, our code that handles authentication, our code that handles dangerous things like re-encoding videos, that's the kind of stuff that a dedicated security engineer might sit there and do security testing against it, look at the source code, do a bunch of stuff. And then for all of the other stuff, you're trying to use automation to give you coverage across all of it. Automation can be automatic scanners and fuzzers that will automatically test and simulate some of that. They can be source code scanners that tell you these are patterns in the code that we think are very dangerous. And so this is a constant battle for product security teams at companies to try to get as broad coverage of 100% of everything while going deep in the right areas. We're obviously up against the attackers who actually want to break in. They generally have less information than us, although in a lot of cases it's not actually a huge problem. In the case of shipped software, where you're actually taking software and you're sending it to people's phones over an app store, or you're sending DVDs out or whatever, having downloads, the information asymmetry between attacker and defenders are actually much smaller than people think. The truth is when you're looking for security bugs, the binary code, the object code, is the truth. Source code can lie to you. And there's a bunch of great examples of situations where people have looked at code in source, and it looked fine, and once it was compiled, it wasn't. And that can be because people have, some of the bugs can exist in the libraries that you're pulling in, and you don't, like the printf, everybody knows about the printf bug now, but there are a lot of situations like this where people don't really understand what code is running underneath. You can have interesting compiler issues. So when I was a consultant, we had an interesting problem at a big commercial software company where 2 different teams added the same memory management optimization to their preprocessor for their compiler for their entire product. And what this ended up doing was creating a exploitable malloc use after free, basically a situation where you can do an integer overflow into a malloc in every single malloc in their entire code base. Because 2 different teams have replaced different parts of malloc without talking to each other, right? And so in that situation, the people who wrote the code themselves were calling malloc correctly as long as malloc was what they expected 2 other people had done it. And that kind of thing you see all the time in situations where you have thousands of people working on the same code base. So in situations like that, that code, we found it by looking at the binary code and looking at it in a disassembler. The object code is true. This also comes for like looking for backdoors in crypto. One of our subsidiaries, WhatsApp, recently shipped end-to-end crypto in their mobile app, right? So now we have over 1 billion people who are using end-to-end encrypted. And the kind of common response from the security industry is, or for people not in the security industry, who think they're in the security industry, who hang out in parts of Reddit that make them feel like they're part of the security industry, is that I can't trust it because I don't have source code. And the truth is if you look at the history of this, it is very easy to build crypto backdoors especially into code that is very hard to find in a source code situation, but that is obvious when you look at code, or not obvious, but maybe a little easier to find when it's actually running on the, in a process that you can control. And so my response to that kind of stuff, if I can't trust it unless I have source code, is you can't trust it if you have source code, right? Like if you want to trust that a piece of cryptography is not intentionally weakened on a piece of software that you're using, then you have to look at the binary code as it's running on your system. And obviously that's not like a practical thing, but that's just the truth of how trust works in the modern environment, especially an environment where all of your mobile devices have these big binary blobs that are being downloaded every day. That you download another 5 new binary blobs of updates for all the apps on your phone. In that situation, having source code actually doesn't give you very much trust at all. And so attackers have that benefit. They have less of information asymmetry than you might think. They also only need a handful of flaws. They don't need to have 100% coverage, right? Like, their bosses are fine as long as they find those 5 great flaws. The bosses don't care if they don't find the extra 2. The interesting thing that these guys have is a disadvantage, especially in the online service field, is they need to find these bugs without us figuring that out. And so a lot of techniques we talked about are very stealthy if they run on code that you have in your possession in a computer you control. You guys don't have a copy of Facebook running at home, right? So if you want to find a security bug in Facebook, you have to do so by exercising the software as it runs on our servers. And that gives us the opportunity to then look at how our software is running and to see whether or not people find bugs. There have been situations of big web companies finding a bug because somebody else found it externally, alerting on that, and then having the bug patched and fixed before the person even reported it, right? And generally we'll pay that off in the bug bounties. But that's the kind of advantage we have, and that's something that disadvantaged hackers have because in an online service situation, because they don't know what's running on the other side, they can't just attach a debugger, they can't just disassemble it and look at how it works. And then in the middle, for various reasons, you have people who are researchers who are trying to find bugs. Now, the vast majority of people who are doing security research are doing so because they think it's fun, and it's intellectually challenging, and that they're doing the right thing. And that is actually a much easier thing to do now than it was 10 or 15 years ago. It used to be that most security research on popular products was in a very legal gray area. And there's a crazy history of legitimate security researchers being arrested and charged with very serious crimes for just doing what they thought was right, even if they reported the bug to the company and did everything they could to protect users. Fortunately, we're living in a little bit of a golden age of the relationship between big software manufacturers and security researchers. This is mostly reflected in the bug bounty programs that all the big software companies run. So for example, we had about 12,000 people report bugs to us last year. We fixed a little over 1,000 of those. Is that right, Jay? I think? Yeah, a little over 1,000 of them. We've paid out over $4 million to bug researchers over the last several years. And so, and some of the guys who've done the biggest $20,000, $30,000 ones, we've hired them full time. So one of our best security engineers is the guy who actually reported a really cool bug to us that we thought was so awesome that not only did we pay the amount of money that he made the local newspaper in Brazil for being a guy that made all this money as a teenager, but then we offered him a job when he graduated from college. And so there are a lot of great options for doing security research in a way that then you help people out and you make money. Clearly, though, there are also people who are doing security researcher and then are keeping the bugs for themselves for whatever purposes, or they're selling them to people that they know are going to do bad things with them. Technically, in some cases, that might not even be illegal, but that is a very dangerous path to go down. In fact, there's a guy I used to work with at a consulting company who was indicted and ended up committing suicide while he was waiting for his trial because he had sold the bug that was used in a break-in at a major retailer to steal millions and millions of credit cards. The government argued that he knew what it was going to be used for. He argued that he didn't. Generally, if you're making an argument with the government in front of a judge, you've already lost, right? Like, that's not the place you want to be. And so, this is a place that definitely, if you're interested in the security research, you should be very happy because you guys are growing up in a time that you could do so very legitimately. I would just be very careful not to get lulled into a false sense of complacency by the positive steps that have been made that you can just do this without any thought as to what the impact is. Cool. So let's talk about some real-world defense. So if you're interested in doing defense against these kind of bugs in the real world, it turns out that you need to kind of think a little bit differently than when we look at the bugs. From my perspective, a lot of the security research that we see on a day-to-day basis is not grounded in live reality. What you should be grounded in is either the real-world problems or the real-world attacks. So if you want to protect individual people, normal people who are using products day-to-day, then what you really need to think about are the problems that are actually causing the most harm. And the truth is those cool bugs that I showed you are generally not part of that. The number one cause of people having bad things happen to them on the internet is that they use the same password everywhere. And so they use the same password on 20 sites. One of those sites will be compromised. That site will have not hashed their passwords or used a very weak hashing algorithm. The attackers will now have their plain text password and can go log into the other 19 sites as them and take over their accounts. This is a full-time business for people that all they do all day is buy credentials and then monetize them by having big systems that will go automatically log in with those passwords, reset those people's passwords to lock them out, and do whatever monetization scheme. Now, if that's like a PayPal account, it might be stealing money directly. If it's something like Facebook, it's generally spam, that they'll post spammy links. So if you ever see your mom or your uncle or somebody all of a sudden having not safe for work images that they're posting that are obviously meant to catch people's eyes, to click on the links, that generally means that they reused their Facebook password somewhere else and they had to compromise on that other site. If you're thinking about doing defense at kind of the higher end and you're looking at defending enterprises, then it's really important to think about the actual attacks that are in the wild and the capability of your attackers. For a long time, there's this real feeling in the security industry that defenders have to be right every single time and attackers only have to get lucky once. But the truth is, if you look at like a real successful attack, if you look at somebody breaking into a company like ours, moving through the network, finding the information they want, and then getting out with that information, and especially getting out without getting caught, then a lot of things have to go right for them. And in the defense side of security, we're starting now to use a terminology that we borrowed from the military, which is the idea of the kill chain. So in the military, the kill chain is the things that have to happen before you blow something up, basically. In the online world, the kill chains are the things that an attacker has to successfully do before they can fulfill their objective. And so we're going to have to go this into too much detail. This is an interesting paper that you guys, all these URLs are obviously in the PDF that Professor Bonet posted. Interesting paper of looking at the different kinds of things an attacker has to do. But my suggestion here is like when you think about things in the enterprise, it's not really about that really sexy initial bug. What's really interesting in the enterprise context is all of the steps after. The initial bug only gets you usually number 4, maybe number 6, right? These are where you're using flaws in software to get around controls that are in place. The rest of them are about being careful, about having good preparation, having good operational security, having the right people involved to know what they're doing, and knowing how companies work on the inside. Those are the kinds of things that actually separate the really good adversaries from the not so good ones. And those are the kinds of things we think about from a defense perspective. Because the truth is, on a network our size, I cannot keep bad guys from that initial step of exploitation, right? The truth is that we will always be running software that is vulnerable to exploits that allow them to initially get in. The realistic thing that we have to do is you can't build a system that's brittle, where if you get through the outside, it's all a smushy inside. You have to have multiple layers of defense, and you have to think of all the different things an attacker has to do, and make all of those as hard as possible, and then have systems that go listen on the network and listen to hosts and watch what's going on to make it as likely as possible that you catch them, before number 7. Because that's the great thing about defense, is if you caught the bad guy before they get to number 7, you've won, right? And that's the defender's advantage, and that's how you have to kind of think about this stuff. If you think about the whole, like, attackers only have to get lucky once and defenders have to be perfect every time, then you'll just never get out of bed, right? This is too depressing. And so the reason a lot of people don't think about this kind of stuff, though, when they do research, both publicly and privately and in academia, is that the incentives point the wrong way. A lot of people in security think that security is being scored like the East German judges scored gymnastic competitions in the 80s, which is a joke that none of you get, because none of you were alive when East Germany existed. But there's this idea of like gymnastics and having like the difficulty score, right? That not only did you do something well, but you tried something that was really, really hard. And so it's not the outcome as much as the difficulty. And that's what gets people applause in a lot of security circles, is if you do something that just seems actually really complicated. And the truth is, real attackers don't like complicated. If you do something complicated, a lot of things can go wrong. If the attackers were gymnasts, they would literally, like when they do the vault, they would go, like the vault, like the guys are doing it and they're doing flips and stuff. Like a professional attacker goes up, if their job is to get to the other side of the vault, they walk up and then they carefully walk over it. And then they keep on going. Because they don't care if they get a 0 on the difficulty score, as long as they get to the other side. And this is something that isn't really well understood in either academic or private research, I think. And which is a result of, even the best conferences. This is the proceedings from Usenix, which is one of the best conferences. There's Easter egg in this listing. If you look through, this is all great work, but not all of this work is actually ever going to be, are these attacks that would ever be called used in the wild, or defenses that would ever be possible to deploy. But the incentive to get here is you have to do something that nobody else has done, and if you do it in a way that looks like it was really hard, then that gets you a lot of plaudits, right? And so I'm not criticizing anybody specific here, certainly not my host.
Yeah.
But Usenix is considered in many ways the most practical of all the academic security conferences. And still, even in the Usenix space, I would say maybe a quarter of the papers that are accepted will end up being on a topic that we might ever actually see in the real world. This is why we sponsor a thing called the Internet Defense Prize. So we've been sponsoring a Unix paper for, I think, $100,000 is the prize for the paper that has like the best real world impact. And so we're hoping to continue to do that kind of stuff to try to drive people to not go for the high difficulty score. So what kind of things can we do to protect people against the normal bugs? This is an example of, what's wrong here with this page? Is this really Facebook? No. Yeah. So you can see from the URL, this is running from Dropbox. Dropbox has this fantastic feature where you can upload HTML and then people can view it, which is awesome. Thank you, Dropbox. This is from a phishing campaign that was against our users, a real phishing campaign. And what this did was it played on people's expectation that every once in a while companies will tell them their accounts are locked and they have to unlock it. So if they clicked on the link in the email, which in this case, sometimes that email has like basic misspellings and such, and it's not very effective. This email was perfectly written with perfect English. It looked like a legitimate Facebook email. The URL they sent it from, the domain kind of looked like a domain that we might own. If you clicked on it, you landed on this, and if you put in your email, your password, your birthday, that information goes elsewhere. And then they, obviously the bad guys can then use that information to log into your Facebook account and do all kinds of bad things. This is a very common problem for us. It happens every day, hundreds of thousands of times. And so as a result, when you deal with the real world problems, there's not some kind of really a magical solution for this. You have to kind of grind out a very difficult solution, which in our case is we have a very good account access team that looks at this kind of stuff, and a team called Site Integrity that works with them, that have built a pipeline that even if you log in with the right username and password, that is only the first step of actually getting into Facebook, right? So we see you come with your username and password. We look at a bunch of other pieces of data that we get of what browser you're using, what language is it set to, screen resolution, what kind of network are you on, right? Are you all of a sudden on a phone network that doesn't make any sense for you? Are you physically in a place that we've never seen you from before? And then it puts a risk score together based upon all that stuff. So none of those things are things that shouldn't change for a legitimate user, but if most of them change, that usually means something's wrong. So if it's legitimately your computer, and we have seen that computer before, and you're using the browser you always use, but all of a sudden you're in Italy, we're like, okay, you're on vacation, not a big deal. If all of a sudden you're in Italy, and your browser language is Romanian, and you're using Firefox, and you've never used Firefox before, and we've never seen you before ever, then that's the kind of thing that we are going to kick you out to this next extra authentication check. Of which there are a couple different options for us. One of the problems here is trying to come up with things that only the legitimate person knows, or very few people know, that isn't easily phished, right? And so this is the problem that we see over and over again with these authentication checks, is if you ask people for an extra thing, then the people that do the phishing will just ask for it. You saw in that case, they asked for your birthday, right? Which I think used to be a question that we'd ask people to verify their birthday. And so this is a situation what we do is we reach into photos that have been posted by your friend, and you've been tagged with that friend, and you say, which of your friends is this? And we ask you this 5 times, and if you can identify which of your friends, out of the 6 choices, this person is 5 times in a row, then most likely that is you. It is very unlikely to be a random attacker. Now, where this breaks down a bit is obviously if somebody's like a good friend of yours, or they're a family member, then they might know 4 or 5 of those people as well, right? And that's problematic, and this is where this becomes kind of a problem for the entire industry, is finding things that somebody knows that nobody else knows. That's the idea of a password, but it turns out people are willing to put their password in anything all the time, or they use the same password over and over again. Other people have better solutions that aren't available to folks like us. We have about 1.6 billion users on Facebook. And that doesn't include Instagram and WhatsApp and all that other stuff that we own. Clearly, we can't do something like have people call us or we give them a phone call. I know like the banks, if they really lose track of you, will just shut off your account because they have your money. And eventually, you will go in to a bank branch and you'll say, I want my money back. And they'll say, oh, thank you. Show me your ID. I'll unlock your account, right? We don't have any bank branches. And so we have to find things like this that are a little more unique. So, yes, sir.
I have a question, but isn't that still vulnerable to phishing? Because if this is what you present to the attacker, can the attacker just turn around and say, oh, I have this question, I'm going to show this page because I talked to Facebook, I try to log in, they
Yes.
say I have an extra authentication.
Yes.
And he goes back to the user and says, oh, which of friend is this? Okay, it's Zgen, and he comes back, and so
Right.
basically, it's an extra step.
You're absolutely right. This is vulnerable to phishing. Basically, nothing we can do is invulnerable to what you're talking about, which is a relay attack, right?
Okay.
If I have you actively using my site while I'm talking to another site, it is extremely difficult for me to find a way that you will not get secure. We have some protections against that for ourselves, but we can do those because we're an enterprise and we do things like give people their corporate phone or give them little security tokens that can have cryptographic identities built into them. We obviously can't do that for people worldwide. So you're right, this is vulnerable to relay attack. The truth is, though, the vast majority of these attacks are asynchronous. They're not synchronous with you being on that moment. They're either, these people run a phishing campaign, they gather up hundreds of thousands of credentials, and they use it somewhere else, or they probably sell it. There's a lot of specialization in the black market here, where there are people who just gather up credentials, and there's people who just use them to monetize, and they're often not the same people. They have different skills. Monetizing actually requires usually kind of an organized crime mindset because you have to be able to, you have to have these business relationships, you have to be able to move money around the world to launder it. The credential theft is actually in many ways much easier. Most of the people in here would have the technological skill to go do credential theft at scale. But none of you guys, I'm guessing most of you don't know mafiosos who will launder the money for you, so you probably specialize on one part of the equation and then go sell that information. So in that case, this works great for us, because this only works in an asynchronous situation, and you also can't do this at scale. So if you've stolen 100 million passwords from some other website, and 10 million of those work on Facebook, you can't get 10 million people all at once to be online. And also, if you're doing a relay attack, we can detect that, because we're seeing the connection that comes from you. So if all of a sudden we see this one server, that all these people, this server is like in Brazil, and none of these people are from Brazil, and it's proxying all their connections, and they're logging in from it. That's the kind of thing that we can see and stop, and then every login that comes from that IP becomes suspect. So this works in React. It's one of the things that's not perfect, but it's good enough to stop people from doing it in mass. Yes, sir.
Wouldn't two-step authentication with some sort of push notification also prevent relay attacks?
That's right, and we do have two-factor authentication. We'll text you, and we have push notification stuff. This is for people who haven't done it. Unfortunately, getting people, it's very hard to force people to turn that stuff on. There's also a number of interesting cultural and technical issues that make that it works great in the US and not so great elsewhere. For example, in India, people have very poor delivery of commercial SMS because there's so much SMS spam that the networks do a lot of filtering, right? And so it's difficult for us in some places to do that kind of stuff. And then forcing people to do like the two-factor and such. Ironically, people will say like, I don't want to give them my phone number because that's not secure. It's like, we're just trying to keep you more safe, we're trying to keep your information more safe, but it's a hard thing to explain to people. Yes, sir.
Yeah, this problem is like so easy because you can tell by the name the vicinity of that group, that person. So
Right.
it's like even an attacker can like get all the problems right just by analyzing the last name of the choice.
Right. And so that's why we do it 5 times. So to make it less easy for you to do that, or to like Google image search people, and 5 people are the same one. But you're right, we do have, it's not perfect. This is something that the security industry has a lot of difficulty accepting, which is imperfect solutions are generally good enough. And that we have to accept imperfect solutions, even if we can come up with mental holes in them, because that's a lot better than not doing it at all. Right? Okay, I'm going to move forward because I want to get through this and we'll have some time at the end. Sorry. Okay, so if you guys are looking to do interesting research, some places where I think that there is either do research or from a commercial perspective, start a company in the next couple of years, there are some open things that are very practical. The first one is network security at scale. So the entire kind of history of network security products that companies buy is based upon the idea of having choke points that you can run all of your traffic through. That's a choke point through which a firewall goes. It's a choke point for a web application firewall. It's a choke point at which you can place an IDS sensor. This is a diagram of what our production networks look like. Where is the choke point here?
Yeah.
There isn't one. Every single one of those lines is a 40 gigabit or 100 gigabit fiber optic link, right? And the truth is that modern networks have a huge amount of what's called east-west bandwidth, which is bandwidth between different racks, and then as well as good north-south, which is in and out of the data center. And that's what you're seeing here is a highly redundant network that has a huge amount of bandwidth from any point in the network to any other point. The flip side being that there's no place to put layer 3, layer 4 access controls in, or IDS sensors and such. And so this is we have a bunch of solutions that I'm not really going to cover here, but this is an interesting problem because while we are obviously a little more on the edge with our network design, this is where every company is going to be in 10 years. Not because they're building this data center themselves, but if they're currently up at Google Compute Engine, if they're using Amazon Web Services, if they're using Microsoft Azure, they're running in a data center that's laid out like this already. So a lot of companies don't understand that they're already in a highly flat data center that doesn't have a lot of layer 3 access controls because that complexity is being hidden by the cloud computing provider. The other thing that's going on in the security world that really there hasn't been a lot of recognition, I think, on the academic side, is we're moving away from making decisions at the moment, and we're moving towards making decisions later, right? And this is because in these kinds of networks where you're running at huge scale and highly distributed, you can't have all the information in front of you to make a decision fast enough. On a 100 gigabit per second network, there's something like only 6 or 7 nanoseconds between Ethernet frames, right? So that's like the amount of time it takes light to move like 8 feet or 7 feet or something. So if you have a security device and it's looking at an Ethernet frame, you have basically until light gets from there to here to make a decision of whether or not you're going to let it go past. And it's hard enough to build systems, and all they do is take that packet and route it somewhere. It's extremely hard to look at that and make a security decision. So what we're ending up with is gathering up information from lots of dumb sensors instead of smart systems and then making decisions later. And so you use big, flat storage mechanisms. This is a rack from what's called the Open Compute Project, which is what Facebook uses to, is an open project by which we open source our designs for our data center hardware, and we let anybody build them, which gives us all kinds of economies of scale, and it also helps us push people towards building more efficient data center designs. So this is what our storage systems look like, lots of hard drives in these racks. And then GPU compute clusters, this is what our GPU nodes look like. As you can see, there are 8 very expensive, very hot NVIDIA Tesla GPUs in there, GPUs. And so on top of big amounts of storage and machine learning networks powered by GPUs, you can then build big storage mechanisms in real time, data collection like Apache Spark, data processing like Apache Spark. MLLive is a machine learning library for Apache Spark that's pretty popular. And into that system, you're dumping dumb security sensor information. So at the multiple 100 gigabit speeds at which big Russian networks operate, you can't really make a lot of inferences from the network at speed. So what you have to do is record net flows and their information and then stream it into storage. Logs from cloud providers, host instrumentation from Chef. This is OS Query, the project we have. Carbon Black from things like laptops, from your IT systems, and then from your threat feeds, and then run software here to make inferences and make decisions of whether or not something bad happened. This is where security is going. In the old day, what you would do is each one of these things would require a different security product, and it would make a decision in real time. And then we're just past that. Like, you can't build things that are fast enough to be distributed like that. And the truth is if an attacker is hitting you for all the different parts of the kill chain that we talked about, then you 2 or 3 of these places are going to have pieces of data that make it obvious to you that an attack is going on, and that'll be useful for forensics. And so this is an area that I haven't seen a lot of good academic research on, but I'd love to see like machine learning algorithms running asynchronously on open source standard storage systems like Hadoop to make inferences about security issues. Okay, great. So now we'll come to the part that will hopefully make you money. So I'm glad you guys stayed. You guys were lucky. Can we cut off the live stream to other people so that the students did show up? Don't get any advice. It's not great. Okay. I'm glad that you guys, some percentage of you, I hope are interested in this area as a career, as a field. I think that's exciting because, like I said before, I think in the 21st century, information security might be one of the most impactful engineering disciplines in the world, right? Obviously, there's a lot of people doing important work in different fields of engineering, but when you think about changing human history over the next 50 to 80 years, information security has as much a play as anything else. If you want to choose to, you can enter this field and you can do some really good things. You can protect people who can't protect themselves. You can protect, democracy activists in countries that have nation-state level adversaries targeting them. You can protect just normal people who are trying to be monetized by organized crime. You have that choice to be somebody who stands up for those who can't defend themselves, and that's a pretty powerful thing. Not most civil engineers don't get like a choice like that, right? And that's like a cool thing about going in this field, is that you get to choose who it is you're defending. You can bring voices to people who've never had it. Obviously, we're in an era where nation states now rise and fall based upon the communication of their citizens on social networks and communication mechanisms out of their control. So for the first time in history in some of these countries, people have the ability to communicate with each other and talk about politics safely. But in doing so, they put themselves at risk because, again, they're facing well-financed and well-trained adversaries, and it's up to us in the InfoSec industry to help protect them. You can secure technologies that billions of people depend upon. You can stop people from using technology to oppress those. Like, the internet doesn't necessarily have to be this wonderful democratizing force. It can be used for oppression and control. And those of us who are part of this industry can decide against that. My point here is that being part of InfoSec makes you a moral actor, right? So you can't, if you're going into security, which again I think is a wonderful thing, you have to realize from the outset that the decisions you make every day will have an impact on other people, and that there's a moral and ethical component to that. And again, that's true of some fields. That's true of like medicine. Now it's clear in medicine. Medicine has these basic ethical rules about what you do to help people, and I think they have, in some cases, their gray areas are a lot further away. Whereas in the InfoSec world, things are much more dynamic, and it's much harder to know what our gray areas are and whether you're doing the right thing or not. And so, my advice really here is that you guys are all Stanford students. You have a lot of opportunities. You have the opportunity to choose to do something that you're proud of and that fit your moral and ethical choices, not vice versa. That's not true of 99% of the people on this planet. They do what they have to do to feed themselves and feed their kids, not you guys. And so you should take that gift and you should use it to make choices to do the right thing in cases. And so we can talk a little bit afterwards. I've got some examples of this, but I think you guys get the point. 6 career tips for you guys. First, I often get asked, what should my first job be? Should I go work for a big company, go look for a small company? My suggestion here is, what you should do is you should look for places, jobs where you are uncomfortable because you don't think you can do it, right? If you're in a job and you're phoning it in 10 to 4, and you're like, man, I got this handled, then you are decaying. you are slowly dying in the Buddhist sense, right? And that is not, in this field, or in any tech field, that is not a place that you want to be. Always put yourself in a place where you think you're going to learn the most, and things are going to be hardest for you. That can be at a big company, it can be at a small company. There's a lot of other factors that go into it, personality and such, but whatever choice you make, don't make the comfortable choice. Second is when you pick a career, my suggestion is always be part of the product, not the plumbing, right? So if you work for a big company, the toilets flushing is a big deal, that company being successful, right? Clearly, if indoor plumbing did not exist, then big corporate campuses would not work. They would be pretty horrible places. But does anybody go and thank the people that make that work? No. You expect it to work. And when it doesn't work, you flip out and you complain about it, right? You don't want to be in the same place in IT and technology where there are a lot of companies where IT is important, but when they say that, what they really mean is that technology is part of the plumbing, and they're only going to notice it when it goes bad. If you want to be in a position to have the most career growth and most career options, you want to be part of the product. In security, that means being either that specifically your company is working security, or it's a company like ours, where security is like a fundamental part of the company existing. Therefore, you are part of the product because the product we ship is trust, right? And so if nobody trusts us, nobody uploads anything, and therefore we don't exist. And so you want to make a decision to be part of the product. The third one is the point of maximum leverage in any negotiation for a job is right after you've been offered a job. This is where I see geeks make the most mistakes and leave the most amount of money on the table, is at the moment that somebody offers them a job, they are so incredibly excited about it that they either accept it immediately or they make it clear that they're going to accept it immediately. This is advice I'm going to give you. You can take it or leave it. But I would suggest always thinking about, and in most cases, asking for more compensation whenever you get offered a job. And this is for a couple reasons. One, the person you are talking to when you get a job offer is not the person who's paying you generally, right? They're a recruiter. Their job is to fill that position. They have gone through hell of looking at thousands of bad resumes and having dozens of people interview until they picked you, and now they've chosen you, and they are so close. They're so close to having this position filled, and all they have to do is to get you to sign on the line that is dotted, right? This is your point of maximum leverage. And what recruiters generally have is they have a budget, and do they come to you, do you think they offer you on day one, this is 100% of the maximum amount of money I can offer this person? No, that would be idiotic, right? They always hold back a little bit that allows them to have some negotiating position. And so that's the time that very politely, and with caveating, I'm very excited about this job, this is fantastic, but I think my market rate is blank, you can ask for more compensation. At a big company, that can be either stock or dollars. I would recommend stock. At a little company, it's always stock. At a little company, you should never ask for more dollars, because at that place, they might actually have a hard cap. It also demonstrates that you don't understand where value is created in that company. So in any situation, if you get offered a job and there's a stock component, I would probably push on the stock. The other reason you want stock is at these companies, you'll get, if you want to make money over a multiple year period, you will get stock refreshers, so you will get more stock. That will be based upon how much stock you got in the beginning. So if you ask for that more money in the beginning, you will compound that if you spend multiple years at that company. Don't let that moment go to waste. And that's what I see a lot of people letting it go to waste. And honestly, this is especially for the women in the audience, you should have confidence in yourself that you are, that they want to have you there, because this is where I think a lot of the comp inconsistency in the tech industry comes from, is that in my experience, I've hired several hundred people in my career, it is much more likely that the guys will negotiate for more money than the gals. Fourth one is if you take money from a private company, understand the capitalization table. There's a thing called preferred shares. They are better shares than the shares you're being offered. If you don't understand that, then you just got played. If you ever go into a meeting with anybody, you should know and visualize what you want the output of that meeting to be. That output might just be, great, I want to get an update on something. But this is just like good advice. If you go into a meeting with somebody, know what you want out of it, because generally a meeting is actually a negotiation. And the sixth is being nice. So this is a very small industry. And if you work in a sub-industry like security, it is really, really small. Every single day I run into people or I interact with people that I work with in previous companies. And there's a famous old saying that I'll make more polite, which is be nice to people on the way up. If you're mean to people on the way up, they will be very mean to you on your way down, right? And one of the great things about Silicon Valley is if you build good relationships and people trust you and like you, you can try and you can fail and you can try again. If you treat people like a jerk when you're in a position of power, that will not happen. And I have seen that happen multiple times. So just be nice to people, be good people, and you'll be a much happier person. Anyway, those are my advice. Career advice. I'll be around if you guys have any more questions.